Good afternoon, everybody. It's nice to be back again. I did a talk earlier about the return on investment of built-to-last equipment, and one of the topics that actually came up in that was curing. So I'm here today now presenting on behalf of Kraft Curing. Unfortunately, the presenter fell ill, so I'm taking his presentation and presenting it. I'll do my absolute best, but you're in good hands, as I also have specialist knowledge around concrete curing, as it is a critical part of all concrete equipment and the manufacturing process of concrete products. So let's go straight into it. Kraft Curing are one of the leading curing solution providers in the world, and they have been in the market for several decades, providing solutions to all forms of concrete products, or concrete manufacturers producing concrete products. So I'm Quintin Booysen from PMSA in South Africa, Johannesburg. So why do we do concrete curing? Firstly, it produces a better quality end product. It has faster production, and what we mean by that is concrete takes time to set and get hard. So the quicker we can cure a product, the quicker we can free our boards, the quicker we can free our concrete molds, the quicker we can continue with construction. Whatever the concrete product is that you're producing, the quicker we can do it. So the faster the production cycle. Better concrete curing results in better strength and cement savings, because if you can produce a concrete product quicker and stronger with less cement, we ultimately have a cement saving. With concrete curing, you are in full control. There are also energy savings. And how do we get energy savings? Because concrete, when it hydrates, produces its own heat. So if we have a good concrete system or good concrete curing system, we can capture that free energy and use it in the system. Higher flexibility, because we have the adaptability to change molds, to move products quicker. So we have all the flexibility when having a good concrete curing solution in our production process. How does it all start? Well, one of the bases of any concrete is obviously cement. We need cement. Without cement, we can't make a concrete product. And cement, as we all know, is a very fine product. It's like powder. It's normally around 45 microns. And here we have a cement particle that's probably blown up, I would guess, about 500 times, maybe more. So you have this particle. We then add water, which is in the concrete process, and the water gets into the structure, and chemically it starts changing from a solid into a gel formation. And that gel is critical because the gel is what ultimately becomes the part of the matrix, the glue within the structure of concrete. This is a zoomed in several, you can imagine it went from 45 microns, and here we have something that's about 10, 15 centimeters. So under a microscope, we are looking at the gel formation, the little fingers that start coming off on concrete, inside of the concrete, between all the particles of sand and all the particles of other materials. You have this incredible gel structure that starts forming, and these little fingers start crossing across to each other, and they are the basis for the strength that you're going to form with inside of your concrete. Well-graded concrete is critical. So on the left-hand side here, we have a structure that's made up mostly of large particles of aggregate, stone, and then small particles, your sand. And in between all of that, we'll have the cement. Now, on the right, that's on the left-hand side. On the right-hand side, we've added in extra particles, which is critical to get a well-graded concrete. You want that because you want your cement to be able to cover more particles or more aggregate. And when you have a lot of fine material in concrete, your cement has to work so much harder. It has to be spread over so much greater area, over every little particle, to generate strength. So when you have larger particles and well graded, the cement has a greater chance of creating a stronger concrete in the end. Moving now in, so we've gone in, here's your coarse aggregate. This could be a sand particle. and the water and your gel structure that we spoke of earlier. So what it starts to produce is you have your Portland cement plus the water, and that generates what we call calcium silicate hydrate, or more commonly known as CSH. And in between all of this, we have the CSH forming. We also have water, which is a free water floating around. That's the water that's sort of left over from the hydration process that's hydrating the cement. And we have a byproduct, which we call free lime. Free lime is your calcium hydroxide, which is down here. That calcium hydroxide is not giving any significant strength to the concrete in the early stages. Later on, it may bind with other fly ash or other products, but in the beginning, it's more just floating around. That's why we call it free lime. That free lime it's susceptible to chemical attack, and it's also can be deleterious. It can be moved through to the surface of the concrete, which later can come into what we call efflorescence. So what is efflorescence? It's really the migration of those salts to the surface of the concrete, and then it's met with carbon dioxide, and you end up with a product which we would call efflorescence, a calcium carbonate. And it can be unsightly, although it's not normally, doesn't normally change the strength of the concrete, but it is unsightly. And people looking at it on concrete roof tiles, especially where you start having white patching, or on paving, it's often not looked upon in a positive light. So what are the conditions of efflorescence? There must be soluble salts available. Now, in our case, in the concrete, we have the calcium hydroxide, which is in this water. Well, the next one says there must be a source of water in contact with the salts, forming a salt solution. So now we have this product floating in between all the little micro cracks, in between all the capillaries, and that then moves through to the surface. So if there's evaporation, we start getting the salts percolate or moving towards the surface through this capillary action. So there must be a pathway for the salt solution to migrate to the surface and evaporate. So the water evaporates, you're left with this calcium hydroxide on the surface, which together, I'll go to another one. Here's a bit of a better presence. It comes on the surface of the concrete, and that together with carbon dioxide will form your calcium carbonate. And the water would be free, the water would evaporate off, and you're left with this unsightly white formation, which effectively is the type of a limestone, a calcium carbonate, carbonated calcium. So if we can reduce if we can reduce the migration of the salts to the surface, we effectively can halt or greatly reduce the efflorescence on the surface of the concrete, because the free lime or the calcium hydroxide just doesn't have a chance to be transported to the surface. It doesn't have a chance to meet with the carbon dioxide and forming this calcium carbonate. So effectively, what we try to do is have a dense as possible product that would reduce the amount of water, or the free water in the system, that would ultimately reduce the moving to the surface, the calcium hydroxide moving to the surface. And through a good quality curing system that can be reduced, and through a good quality concrete, it can also be reduced. So primary efflorescence is that excess water in the manufacturing that is not chemically reacted with the cement is available for the transport of the soluble salts. So it's that free water that's in the system, as we saw earlier with the blue, that this calcium hydroxide is floating around in it, moving around and to the surface. The soluble salts are introduced primarily by the cement, but also can be introduced by the water and sometimes by the aggregate. So sometimes you have these salts forming coming off your aggregates or your water. That's why it's good to have potable water that's drinkable, and aggregates that preferably have been washed in clean water. The distinction between primary and secondary efflorescence is somewhat arbitrary in the first few days. So what happens is we don't really know always, is that through the manufacturing, the free water, or was there other water that was introduced that's pulling the calcium hydroxide to the surface and ultimately forming with the carbon dioxide to form the efflorescence on the surface. So secondary efflorescence is exactly that. It occurs when the water from the outside source, so this could be a paver paved on the ground, and you have water that's not really percolating, but being drawn through the capillaries of the concrete, and it's pulling those salts to the surface, and the surface then, with the carbon dioxide, starts to form a efflorescence on that, or calcium carbonate, like a type of a limestone, almost very micro levels, but it's on the surface of the concrete. So the water is absorbed into the concrete product, dissolves, and it forms within the matrix, and it pulls through to the surface. The drying results in these dissolved salts leaching to the surface, where evaporation occurs, leaving the salt residue behind. How do we prevent this? So, optimizing the mix design. Earlier, we looked at a way of having better graded aggregate. And the better the grading of the aggregate, the less chance of voids being forming, the less chance of water floating about inside of the concrete. So let's try to get a higher or a more dense concrete. So too little optimization in your concrete mix design ends up in a lower density of concrete. Too much cement, in this case, ends up in if you have a high cement percentage, which is often present in concrete roof tiles, where they may have as much as 20% or more cement, you end up with more free lime, that calcium hydroxide. So the higher your cement content, the higher the chance of efflorescence. Optimized water content. So enough for the desired properties. The water content needs to be correlated to the cement. So if you have too much water, you're going to have a lot of free water that's not bonding with the cement particles and through the hydration of the cement. So you're going to have more free water, which will obviously ultimately create little gaps within your concrete, and that will be a transfer mechanism for the calcium hydroxide to start moving through your concrete. Use well-graded aggregate to minimize porosity. Use low alkali aggregate cement, low alcohol cement to deionize the water. This may also minimize it. And the use of fly ash or slag can also be useful in minimizing efflorescence. Other method where we are presenting today is around the optimizing the curing solutions or the curing conditions. So if you cure in the presence of carbon dioxide, which we are able to do through a burning system where we have a vapor system, we burn gas, and the gas forms a carbon dioxide through the burning process, and you have this carbon dioxide floating inside your curing chamber. This is a typical curing chamber. That carbon dioxide will ultimately bond on the surface with the free lime or the calcium hydroxide, forming just below the surface, because it'll penetrate in a calcium carbonate. So it'll effectively start sealing off your concrete around, well, it's not concrete yet, but it'll seal off the surface of the concrete. If you cure in warm, moist environment, like vapor, the concrete has a higher strength and density before it's subject to weathering. So that will also reduce your secondary efflorescence. It also allows, curing allows for the use of higher percentages of replacements, such as slag or fly ash, because by heating it up, we can get the fly ash to bind with or chemically bind with your calcium hydroxide in early stages, and you can get a better or denser concrete quicker. Another method is exhausting. What we mean by exhausting is opening in your production facility. We open the exhaust system and we allow the excess moisture and heat to escape more readily during your curing process. So it's an important part of production that you exhaust properly. Prevention of efflorescence, other methods. Concrete should be protected against external water as long as possible. Good air circulation, allowing sufficient carbon dioxide will promote early carbonation and minimize both primary and secondary efflorescence. So in a good curing system, as we the previous photo, we actually saw there a curing room. We're able to put in proper circulation systems that will allow equal curing throughout the room, equal temperature, equal distribution of heat, equal distribution of moisture, so you get a more even curing process going on. Good air circulation and sufficient carbon dioxide promotes early carbonation. As we've said, good mechanical compaction. So having a good machine that compacts your concrete, or good vibration in your concrete, will also help to prevent efflorescence. There are also other sealants and other materials that can be mixed in, and there are many companies that can also provide these to you. But that's not the discussion for today. That is through admixtures and post methods where we can seal off with polymers and acrylic latexes. Summary on this is on the efflorescence. Efflorescence can be minimized. There's not a single solution. Optimize your mix design, optimize the curing and storing conditions, and follow good building practice. So try to minimize the water coming through capillary reaction with plastic sheeting, backing of plastic. So don't allow too much water to percolate through your concrete, which will bring that free calcium to the surface. What we look at is, so Neville is one concrete technologist, and he says in order to, so we're looking at curing and hydration now. How do we get better strength and maximize the hydration of the cement to get ultimately your highest strengths possible for your cement, for your concrete? In order to obtain good concrete, the placing of an appropriate mix must be followed by curing in a suitable environment during the early stages of hardening. Now, those early stages, we are talking about from the setting of concrete right through to that first 24 hours. That is critical. Curing is the name given to the procedures used for the promoting of the hydration of cement, and consists of a control of temperature and the moisture movement from and into the concrete. The object of curing is to keep the concrete saturated or nearly saturated as possible until the original water-filled pore spaces in the fresh cement paste has been filled into the desired extent by the products of hydration of cement. So it's really giving that cement a chance to fill all those little voids, those micro voids, right up front as the gel formation and the fingers start to grow. For most concrete, active curing stops nearly always long before the maximum possible hydration has taken place. So what do we mean by that? Most concrete is allowed to kind of dry out. We've taken away the presence of water by not properly wrapping, not properly having a curing environment, and your cement is just not allowed to hydrate fully. And that means you've essentially wasted cement in your production of your concrete or in your concrete product. Further, hydration will only proceed if the amount of water present in the paste is at least twice that of the water already combined. So this is critical when you have very dry concretes. Like in our industry, we work a lot with vibrated concrete in brick and block production, paving production, and it's an extremely, or even your hollow core slabs. And so we're not referring too much to your wet concretes, your high slump concretes here, where your cement water ratio is below 0.5. It is of great importance to replace the water that is lost in the self-desiccation or the hydration, and thus a source of external moisture is necessary. So part of that 0.5 water that we have in there, the water cement ratio, part of the water actually gets used up in the hydration process. And we need to replace that with an external source. And that's where a curing system is critical, because it actually replaces where that water is being lost, and it re-adds the moisture back into it to allow the hydration to continue. Curing only really affects the outer surface zone of the concrete. So typically about 30 to 50 millimeters of that concrete, that outer skin. So the inside of the concrete is normally kind of well cured because the water doesn't all escape and it's well wrapped around the casing of the outer skin. However, keep in mind that the durability of the surface of the concrete is of the highest importance. This is the area that is subject to the stresses, the weathering, the abrasion, so the paver, the abrasion on the outside on concrete columns, the freeze thaw, or even just to protect the steel that you don't want to lose. You want to have the highest possible strength on the outside of your concrete. Moisture loss leads to poor strength development, plastic shrinkage, increased permeability, and reduced resistance to abrasion. So you end up with a weaker concrete on the outside, more porous. What is concrete curing? So we've spoken a lot about it. Concrete technologists would, in a summary, sort of say curing is the process of hardening of concrete. But on a site or in a production facility, the production manager or the people in the site would start talking about curing is the process of drying concrete. There is a vast difference between drying of concrete and hardening of concrete. Hardening is allowing the hydration process to fully come into effect, whereas drying is taking away water. They're contrary to each other. So in curing, we don't want to dry out concrete. We want to keep it in a moist state so that the hydration process is maximized. So a curing system or a curing solution would take care of this, and it wouldn't allow a product to dry out. It'll allow a product to cure or harden. What is required? So during the hydration of cement, that is that initial from 2 hours onwards up to 48, well, the hydration continues for quite a long time, but especially in the early stages, there's a chemical reaction and it is giving off an exothermic heat. So the chemical reaction has a byproduct, which is the exothermic heat. That heat is free heat. You've already paid for it in every bag of cement. So a good curing system will economize that heat by trapping it and keeping it inside your system. So inside your curing chamber, underneath the plastic, underneath the sheeting, whatever you're using. And it's critical to use that heat that's free, that you've already paid for in every bag of cement. It's not there when you buy it. It's not that the bag is hot. It's when the water gets added to cement, the exothermic reaction releases heat, and we try and capture that heat and use it to the best advantage we can. Advantages to heat, to do more with less. So it allows your product to turn faster. So in brick and block making, you can get your board back quicker. It economizes the mix. There's a potential to drop cement content and early handling of products without breakages. So the quicker we can harden that product, the quicker we can handle the product. So there are also disadvantages if you speed up the hydration too fast by adding in too much heat, too much moisture right in the beginning in your curing process, especially the heat, you end up with short crystal formation. Earlier we spoke of those crystal fingers that come together. So if we heat it too fast and we allow too much heat, you get a quick strength, but you don't really get the best possible concrete. So it's a balance between strength gain and ultimate durability of your concrete. Curing and hydration summary. Active curing is one of the most important things a producer can do to ensure the long-term durability of their products. The heat speeds up the hydration process. So we spoke earlier, we've got this free heat through the exothermic reaction. We capture that heat and we use that in the hydration process or in your curing room. Moisture increases the amount of cement that is hydrated. So the more moisture after you've made the mix. So in the curing process, not up front, we don't want to put too much water. As we all know, too much water in the beginning when making concrete is not good for the strength, but high water content after that, let's say the 8 to 24 hours is critical because that allows the cement to hydrate. All cement will never completely hydrate, but you have the ability to maximize the utilization of your most expensive component, which is cement, through a good curing system. Now we're going to go into a few curing systems to give you an idea. So this would be the storage facility before it's insulated. So in a brick and block plant, there's several layers here. You can see up to 20, we do up to 22 stages of bricks and blocks and paving. We then cover this whole storage area with insulation and sheeting so that we capture all that heat inside, that we don't lose that free heat from the exothermic reaction. And we use that heat to help accelerate the hydration process and accelerate the hardening of the concrete, especially in those first 24 hours. Where it's not possible to have a storage system, we then can use tarpaulins to protect the concrete and keep the heat inside. So in a very cold environment, here you can see snow on the ground. You can even have this sort of, the exothermic reaction underneath the sheeting may even be producing light steam, you can see the heat coming off it. And that's through a proper curing solution where we may also have had it, in this case, we may have also added external heat underneath, but we're maximizing that heat of hydration plus any additional heat by protecting it, covering it, your concrete elements. So underneath here, you'll have these concrete elements. So the 7 fundamentals of concrete curing. The duration, the longer we can cure, the better. The temperature, the higher the temperature, generally better, although we don't like to really go over probably around 40 to 50 degrees Celsius. You're spending a lot of money for less significant strength gain, and you could even be introducing thermal cracking. So around 40 degrees is sort of the peak temperatures that we use in brick, block, and other forms of concrete, although some people do push it up a little bit higher. But in our experience, over 40, you start wasting money. You're putting in more heat than the ultimate benefit that you're getting. Humidity is critical. We've spoken of that earlier. Concrete needs the humidity to allow the hydration to take place. Circulation to get even curing throughout. Insulation, critical, because if you're not insulating, we're losing all that heat. All the heat is being lost to the environment. So a good insulated curing system is critical. And CO2, we spoke earlier about the calcium hydroxide, which meets with the carbon dioxide to form calcium carbonate. So if we can have carbon dioxide in our system, that's a big plus. Exhausting. We spoke earlier, by exhausting, if you exhaust, you can allow that free moisture that's in the system to get out. You can be in a better control. So that's exhausting your controlled environment. So that's also a critical part of curing. Types of curing. We get natural curing, we get circulatory curing, we get misting, where we spray mist in the air, we get vapor and steam curing, where we're adding heat and energy in through via vapor and steam, and we get non-condensing, which would be using indirect heating. So you'd have heaters that would heat the air, but not directly normally, and that would be non-condensing. So we'd be controlling the relative humidity in the chambers through having a controlled heat and normally working together with the misting to get a controlled environment. A controlled curing environment is essential for increased product consistency, produce higher early strengths, meaning you can strip quicker or you can get your board back quicker, which means reduced turnaround times, provide more uniform colors and strength, produce harder edges on your concrete. We spoke earlier that 30, 40 millimeter, that area on the outside, if we can really get good curing from the start, we get sharper edges, stronger edges, which means more durable concrete. Increased concrete surface density and reduce cement content, and allows for inline secondary processes. So in the brick and block industry, you may want to grind the surface after 24 hours, hammer it, get a bush hammering effect. The stronger you can get your product and the quicker, the more secondary processes you can introduce later. There are different types of curing systems for different products. So paving will have a different system to beams, for example. Product categories, we look at architectural, we look at pipes and water management, and we look at structural elements. So we have a combination. We need to add heat or maximize the heat of hydration, capture it. We need circulation to get even, and we need that moisture to maintain the curing environment. Methods that we can use is the closed room method, which I spoke of a little bit earlier. So we have a room with good circulation, we insulate it fully, and we have really good, so we call it quadric system, where we're controlling the moisture, we're controlling the heat, we're controlling the circulation, and ultimately at the end, we also control the exhausting of the system. When we finish with the curing, we can exhaust it quickly so that we don't end up with water inside, condensating inside of our curing rooms. So that's a quadric system that we talk of. And we also have a vapor generator. In the old days, people would use steam as a steam system. So you'd have a boiler and you would boil the water and you generate steam. Nowadays, we use vapor, where we actually pass the water through a gas burner, and instantaneously you generate low pressure vapor, which is not dangerous because you don't have a boiler that can explode. You have a vapor, and that vapor is very easily controlled. We can spread it around systems. We can put it under tarpaulins. We can spray it into systems similar to the quadrics, where we have a curing room. So a vapor system is ideal for modern curing solutions. And the advantage is you also have carbon dioxide inside of your vapor, which helps with your reducing efflorescence. Other methods are thermal curing, I'd mentioned earlier, where we can actually introduce heat underneath the systems. So we can put it underneath our concrete. So we generate heat, we pump that hot water through pipes underneath, and we put external heat source. But these sort of structural elements, we can use convect air, we can circulate warm air and moisture, we can use vapor, or we can use indirect, which is the thermal curing. Curing and hydration summary. Active curing is one of the most important things a producer can do to ensure the long-term durability of their products. Heat speeds up the hydration process. All cement will never be completely hydrated, but you have the ability to maximize the hydration of your most expensive component, being curing. Cement by proper curing. So ultimately, curing plus heat plus vapor just makes sense. Bringing those together, we have the best possible concrete curing solution that may help you to reduce your costs and increase your turnaround times of your products. Looking towards the future, some trends that are coming around: a single atmosphere versus individual curing chambers. So we promote a single atmosphere quite often, where you have a single environment, and in that environment we're able to capture the heat of hydration more readily. And we spread that heat of hydration around through convection, through circulation fans, and if need be, we can add external heat as well, and even moisture into that curing environment. Lower air speeds, critical, because you don't want to dry products out. You want them to, as we said earlier, we want them to cure, not dry. Another thing is relative humidity of 85 for pavers. It has been found that also helps to reduce the efflorescence, and it helps to just get a better product quicker when you're doing paving. We're also looking at wet side coating. So you may have a case where you want to wet side coat afterwards, a roof tile or a paver or something in the production process. And in that case, we can also adjust the relative humidity in an environment by putting in more heat in a closed environment and having a drier product exiting the system. Inline secondary processes such as push hammering and grinding, that's become quite critical, and covered outside storage areas. There's tents that are available, so we no longer have to just rely on the environment. We can control all of these aspects. So these are just some trends in the market. I thank you for your time, and please, if you have any questions, please post them and I'll try and answer them to the best of my abilities. Thank you, everyone. I have a few questions here. I'm just going to move them across onto my screen. You stress that the quality of water has to be good. How can we get good water? So sometimes your borehole water can be good, but definitely test it, because sometimes your borehole water also can have issues in that you have salts in the ground. So you need good quality concrete. Generally, if you can't drink it, don't use it in your concrete. That's the sort of basic rule. Another question is, follow up. The quality of water affects the quality of concrete. Okay, what can be done by brick manufacturers to minimize efflorescence in bricks? So having a good curing system, having the right cement water ratios, having the right amount of cement in your system. So having a good curing solution means you can use less cement, which means you're going to have less free lime in the system, ultimately less efflorescence. How can already formed efflorescence be treated? Okay, so if you already have efflorescence on there, the best is to leave it. Let the natural acids in our rains and in our environment, let it wash it away. However, some people don't like that. They don't like this white look on their concrete for 2 years, because it can take up to 2 years or longer to sort of naturally degrade. Then you can use acids. But keep in mind, if you use acids to wash away the efflorescence, you're also affecting the surface of your concrete. So in my opinion, the best way to treat efflorescence that's already there is to educate your client that what they're seeing is not necessarily a bad thing. And you can treat it with acids, but you are ultimately reducing the long-term strength of your concrete, the surface. So educate your clients that efflorescence is not necessarily a bad thing. It's just a visual issue, and it will go away with time. So I thank you all for your time. If there's any other questions, please feel free to post them. And visit us at pmsa.com or send us an email. And please do visit us. We have a stand, a digital stand. You're welcome to visit it and interact with any of our sales personnel or our technical personnel. If you need more information, we're available. Thanks once again for your time today.
Thank you so much, Quintin.
Oh, it's a pleasure, Lindiwe.